Okay, we're going to have a look at question 9 to 15 now from the multiple choice. So question 9, we've got to identify the correct graph of how pressure varies with volume for a fixed amount of gas, mass of gas at a constant temperature. Okay, if you see something where you're asked to look at the relationship between two variables, what you can do is see if there's an equation that has these variables on the formula sheet. So if we go to the matter topic, we've got this equation here. For a given mass of gas at a constant temperature, which is kind of describing our situation, there's a relationship between pressure and volume, which is that if you multiply the pressure and the volume together, you get a constant. Okay, I'm going to write that as PV equals a constant on the formula sheet. So pressure times volume equals a constant. And there's only one graph which is going to show this relationship. So effectively, if when you multiply these two numbers together, they have to always equal the same value. What that means is that if volume increases, so if we're moving along the x-axis with an increasing volume, if V is going to go up, in order for them to multiply to still give a constant value, P has to go down. And it has to go down by the same ratio. So for example, if you doubled the volume, the pressure would have to halve for it to still equal the same number. Okay? If the volume was tripled, the pressure would have to go down by a third, or to a third, for them still to equal the same number. Okay? What we call this relationship more generally is that they're inversely proportional to one another. As one goes up, the other goes down, and vice versa. So the only graph here that's showing an inversely proportional relationship is graph C. As the volume is increasing, the pressure is decreasing. Okay? And that's what an inverse relationship looks like. This D is also showing volume decreasing with pressure. Pressure decreasing with volume, but an inverse relationship always has this kind of shape. It's curved that way. So that's the correct answer for C, for question 9. Question 10 is about hydraulic systems, and we've got two different pistons, one with a smaller surface area and one with a larger surface area. And we've been told that we've applied a force of 10 newtons to piston X. Okay, so there's a 10 Newton force here, and we've been asked to work out what the force is F. Basically, as you push this piston in, this piston's going to move out, and it's going to exert a force. If you were to put something in the way there, you could push something along with it. And I'm going to explain, I guess, the simple way of doing this, and then maybe the maths of how it works. So when you get a piston system, a hydraulic system like this, the key thing that we're interested in is the ratio of the surface areas of the two pistons. Okay? So this piston has got a surface area of 4.0 centimetres squared. I'm just going to write 4 centimetres squared. And piston Y has got an surface area of this. Basically, it's a disc in there, right? So the surface area in contact with the edge of the liquid there is 20 centimetres squared. Okay? If you're going from a small area to a larger area, you are going to be multiplying your output force. Okay? So going from a small area to the large area, you're multiplying your output force, and you're going to multiply it by how many times larger the bigger area is. Okay? So because the ratio here, basically 20 centimetres is 5 times larger than 4 centimetres. If you do 20 divided by 4, you get 5. That means that our output force is going to be 5 times larger than our input force. Okay? So the answer is going to be 50 newtons. Okay? If we were pushing y and going the other way around, what would happen is that actually we'd be reducing. So let's say we applied a force to y and then we measured the force coming out at the other end of the hydraulics, we'd actually be reducing the force by a factor of 5. Now, I'm just going to mention that you never get something for nothing in physics, and it might seem like we've just magically made the force a lot larger. The sort of cost to us of doing that is that actually we have to move this piston further, and piston Y is only going to move. So for we'll move by the same ratio. So for every, say, centimetre that we move piston X, piston Y is only going to move 1/5 of a centimetre. Okay, so the force might be 5 times larger, but the distance the piston moves is 5 times less. Okay, so the total energy we're putting in and out is we're not magicking energy out of nothing. Okay, it's kind of the equivalent of using a screwdriver to open a can of paint, like we saw in one of the other multiple choice that we saw in this one here. It's a bit like this situation. It's effectively we can have a much larger output force. If we apply 150 newtons here, we can generate a much larger force on the edge of the can of paint here than 150 newtons, and it's the number of times larger is the ratio with the distances. Okay, so that the output force would be over 30 times larger than the input force, because the distance to pivot is more than 30 times smaller. Okay, so hydraulics are a little bit like levers, but instead of the length of the lever, it's based on the surface area of the pistons. Okay, so the answer there is C. One other thing that we could actually do using the pressure equations, because the key thing inside this tube of liquid is that the pressure everywhere in this system is going to be the same. So if we squash this bit of liquid, because you can't compress a liquid, whatever pressure we exert here, this pressure is going to be the same all the way through the liquid to the other side. Okay, so we've been asked to use this equation: pressure equals force divided by area. Okay, and the pressure at piston X is the same as the pressure inside at piston Y. Okay, it's the same everywhere in the system. So what we could say is that the force at X, let's call that Fx, divided by the area of X, and that is the pressure at being exerted at piston X, is force divided by area. That has to equal the force at piston Y divided by the area of piston Y, which is basically the pressure at piston Y. Okay, because the pressure throughout the system is the same. It's the same at piston X and at piston Y. Okay, and we could use that as our starting point and solve it, and you'll still find we get 50 newtons. So let's just do that quickly. Fx over the area of X. Well, the force at X is 10, and the area of piston X is 4, and that's going to be equal to the force at Y, which we don't know, divided by the area of Y, which is 20. Okay, so that's basically the pressure at X is equal to the pressure at Y. We've just used the equation here. So substituting the numbers in, we get this, and then if we solve that, you should see that we get the same answer. So the force of piston Y is going to equal 10 divided by 4, which is 2.5, multiplied by 20, and 20 times by 2.5, you do that in your calculator, it is 50. Okay, so it's 2.5 multiplied by 20, so the force at Y equals 50. But the shortcut is basically to look at the ratio of the areas. This area is 5 times larger than that area, so this force will be 5 times larger than that force. Okay. Question 11. This one is just a bit of unit conversion. So we've basically been asked what's 56 miles per hour in meters per second. So to convert the units, 56 mph is equal to, well, if we want it in meters per second rather than miles per hour, we need to convert miles to meters. So that's going to be 56 multiplied by 1,609, because that's how many meters in a mile. So that's the total, that would be the total meters per hour, which would be a very big number, but we need the meters per second, so we're going to divide that And rather than it being divided by per hour, we need to divide it by how many seconds there are in an hour to make it meters per second. And the seconds in an hour, 60 in a minute, multiplied by 60 minutes in an hour. So there's 3,600 if you times those two together. So when you put that all into the calculator, you should get 25.028, so it basically rounds to 25. So the answer is A. Okay. Question 12. On your mock, you won't be able to do this to scale because I printed it on A5. So this hopefully is to scale. Well, in fact, even this printing isn't quite to scale. That one should be 4 centimeters long. So what you should be able to do, if you've got a scale diagram, is actually just measure along there, see how long it is. You would have got it as 7 centimeters. 1 centimeter is 10 newtons, so you just times those two numbers together. 7 centimeters times 10 newtons. Well, sorry, no, you would have got it as 7.2. Okay, but this isn't quite to scale. So on the actual exam paper, that would have been 7.2, and then you do 7.2 times by 10, and you get 72. Okay. The other way you can solve it though is just using Pythagoras. So F equals, because it's a right angle triangle, 40 squared plus 60 squared, all square rooted. Okay. And if you put that in, then you should get like 72.1. Okay, so the correct answer is C, 72. Right, 3 to go. Question 13. It's velocity time graphs, and we've been asked to find which of these graphs shows the largest displacement. Displacement for a velocity time graph is the area under the graph. Okay, so we're looking for which graph has the biggest area under the line. Okay, because displacement is a vector and it's how far you are from your starting position, we need to be a little bit careful because the biggest area under the graph is actually B. You don't need to work it out, you can just do it sort of visually, but for B, if you wanted to find the displacement of B, it's done 10 seconds times 5, so the area of that sort of rectangle is 50, so that represents 50 meters on the velocity time graph, and the other one here is the same area, it's 50, except because it's 10 seconds that way, but actually we're timesing by minus 5 because it's a negative velocity, so it's actually minus 50 meters. What's happening is you're going along for 10 seconds at 5 meters per second, then you suddenly stop and start going back the way you came for another 10 seconds. So because the area above the zero line and below the zero line are the same, they actually cancel each other out. Okay, so the displacement S for this graph is 0 meters. They've started back where they finished where they started. Okay, and the same is true for this graph. Okay, in this one they're accelerating for 10 seconds up to 5, and then they decelerate from 5 back to 0, but they're moving back in the opposite direction. So these two, because the areas are above and below the x-axis, they cancel out, and the displacement 0, you'd end up back where you started. Okay, because those two areas are the same size. So it's between these two for which one has the largest displacement, and you can kind of just look visually because they're both up to 20 seconds. That area to me looks larger than that sort of more circular shape, and so A is going to have the greatest displacement because it has the biggest surface area, under the line. Okay. Question 14, we've got object floating in water and it experiences an upward force. What causes this? Well, I'm just going to tell you the answer for this one. So upthrust, basically, the upwards force on floating objects is due to the fact that the pressure at the top of the object is less than at the bottom of the object. So that is the only true statement. Okay. If A were true, then your object would sort of sink rapidly to the bottom if the pressure above it was greater than the pressure below it. the density of the object is greater than the density of water, well, that's just going to cause the object to sink. And then the final one, the weight of the water displaced is less than the weight of the object. Well, actually, the weight of water displaced for any object in the water is always exactly equal to the weight of the object. Okay, so that's how that statement would be true. But as it was false. So B is the answer there. And the final one is another calculation. We've been asked to look at the formula sheet to find the right equation. Let's look at what we've got. We've got a depth, 2.5 kilometres. We've been given a density of our liquid, seawater. And we've got gravitational field strength, G. And we've been asked to find pressure on a submarine at the bottom of the ocean if it's 2.5 kilometres deep. Okay, so pressure is our question mark. So we've got pressure, depth, gravitational field strength, and density. And there's only one equation that links all of those together, which is the pressure due to a column of liquid is equal to the height of the column, that's sort of the same as our depth, times the density of the liquid times gravitational field strength. Okay, I'm going to just use the symbols. So pressure, that's what we're trying to find, equals the depth or height of the column of liquid multiplied by the density of the liquid and multiplied by the gravitational field strength. So we're going to put all the numbers in. So pressure equals the height or the depth. The reason we call it height here is because it's the height above the submarine, but from the top you'd call that the depth of the submarine under the water. It means it's the same measurement. So that's 2.5 kilometres, but we've got to put that into metres. So it's 2,500 multiplied by the density, which is 1,020, multiplied by G, which is 10. And when you times those all together, you get 25,500,000 which pascals, which is 25.5 megapascals. Mega means million, so it's 25.5 million pascals, which is the same as what we've got there. So the answer is D.